Good morning, everyone. Welcome to the Alta 2025 webinar series here at the end of May. I would love to invite everyone who's on the presentation to go ahead and practice using the chat box by putting your name and in what company you work for, and go ahead and list something interesting. So maybe your favorite ice cream in the chat for me. Bob, I see you laughing. Um, just to get engaged this morning, we're all coming out of a holiday, and it's we need to have some fun this morning. That said, please remain on mute during the presentation, and we will answer questions at the end. After you put your name, affiliation, and favorite ice cream, you can also always put questions that come to mind during the presentation, and Bob will answer them at the end. That said, Bob, I'll hand it off to you.
Very good. Thanks, Corey. I hope everybody had a great Memorial Day weekend. FYI, you can see my t-shirt here. I ran the Boulder yesterday in Boulder, Colorado. They had over 50,000 people in the race. I can't say as I had a wonderful time, 90 minutes to run 6.2K, but the leader of the advanced race finished the course in under 8 minutes, which is shocking to me. Or not 8 minutes, 32 minutes, under 8 minutes a mile. So anyway, okay, let's get started here. Just an overview here about Alta. Its whole promotion of this organization is to support laboratory testing, both soils and plant samples to improve profitability. And we're really dedicated, Alta's dedicated to ensuring quality of agricultural data. Now, just a title slide. Corey asked me to put this presentation together at the end of April because we know that the plant analysis busy season is starting to kick up both across the Midwest and on the West Coast. And we'd like to say we're celebrating now, Alta is celebrating 20 years of proficiency testing services. Now, I always like to start this off to kind of a kicker quote here, and that is, you cannot manage what you cannot measure. And the whole premise behind this is to manage any activity, whether it's driving a car or managing your agricultural crop or managing irrigation, you have to have measurements involved. And that's really what the key about our entire industry is providing measurement data. Now, plant analysis, there's approximately 17 essential elements that are fundamental for with mineral nutrition. And it's really optimum for our industries to manage those. It provides the defining nutrient sufficiencies across a spectrum of crop types, be it grain, forages, vegetables, and tree and vine crops. But critical to that assessment is the element of interest, the plant growth stage that's being sampled, the portion of that plant that's being sampled, and the measurement accuracy of the lab analysis. And that's really what the focus of this presentation is, that very last term, that measurement accuracy. Now, here's a chart of our image of the plant essential elements, and we have hydrogen, carbon, and oxygen in the upper left there. We have NPK, which is what we mostly always think about. We have magnesium, calcium, sulfur there as secondary nutrients. We have the micronutrients listed there at the far lower left, and you can see that's quite a quandary of materials. There's 8 elements there, and depending on whose paper you read, and what time the research was done, there's a floating in of elements from that beneficials column over to the micronutrient column. Now, beneficials are elements that are defined that they're not required for reproduction of a plant species, i.e. produce seeds, but have a beneficial effect on the growth and production of those things. Now, there's 6 in this list. If you go to the literature and you look at this, that list probably expands out to maybe 9 or 10. But Dr. Patrick Brown at UC Davis, who I know personally, says, Bob, those 6 are pretty much the identifiers that they consider now to be truly identified as beneficial elements, but they're specific for crops, such as titanium is specific for rice. Cobalt has more or less a need in the very primitive type plant materials. Now, when we look at plant quantitative analysis, I just make this into a gentle breakdown as I see it. And that is nitrogen, sulfur, and carbon total analysis is typically done in high temperature combustion and gas chromatography using gas chromatography separation and detector, i.e. your LECOs, your scalars, your elementar instruments. Now, I say N option is total Keldol. That's really the historic method for doing nitrogen in plant materials. And it's based on an acid digestion with a catalyst at high temperature, and then it measures ammonium either by titration or spectrophotometric analysis. Now, TKN goes back over 140 years, but really it's on being phased out as an industry because of, one, it's a lengthy digestion, and two, it has some pretty nasty chemicals in terms of concentrated sulfuric acid. Predominantly, all the essential elements, P through molybdenum there in that list, that requires a pre-digestion with an acid or a dry ashing where you burn off the carbon and subsequent analysis by ICP-OES. Now, it's truly different from most of our soils analysis in that this is quantitative analysis, where on soils like Malic 3, Bray P1, they're extractable indices, so they're kind of a qualitative analysis. Now, nitrate, ammonium, phosphate, sulfate, chloride, and fluoride there is pretty much, you're looking at the anions, or in the case of ammonium, the cations that are extractable. This is not quantitative analysis, but is qualitative. And typically in our part of the world, acetic acid is used for these things, and spectrophotometric or ion selective electrode for analysis. And I make additional comments down at the bottom there. Direct element analysis by LIBS and XRF. These are evolving technologies. They're relatively new on the landscape, probably less than 20 years each, but they'll probably have a role going forward. Now, when we look at these plant analysis methods that's used across North America, I've listed 17 plus the US EPA 503. These are all methodologies based on what we have in published publications. So we have a SPAC book on methods of plant analysis. We have the we have the SARA 6 manual, and we have the Western States manuals. And these all are quantitative methods. They're basically laid out, as I just said in the previous slide, on either combustion or acid digestion. And then acid digestion falls under two classes, open vessel and microwave. Now, Modis under Ag Gateway have developed a method code library for all these methods. So if you go to the Modis website, you can look at these and kind of pick them all out. The last count I seen on the Modis website for plant analysis was approximately 180 different methodologies there. Now, the reason there's so many is because you have different digestion protocols and different analytical protocols. Now, the LP program is based on submission of 4 botanical samples. I like to use the word botanicals. It's kind of our own coding system. We always talk about the bot analysis when we're talking about ALP in our own circle here. And it's based on those 4 samples submitted 3 times a year for mineral analysis and trace elements. We really pride ourselves in that the way we pick our 4 materials. So we typically have a row crop, a vegetable, a forage crop, and a tree crop in every cycle. So you see one of these 4 in every proficiency cycle. And now mineral constituent concentrations vary by crop type, stage of growth, and provide a broad analytical range. And I say this because I think it's very important that a PT program covers from low concentration to high concentration across the samples that we submit. Now, briefly, I'm going to talk about our sample prep system that we use. We bring in the material, dry material. We usually dry it at 60 degrees centigrade for 24 hours. And then we either use a high-speed mill or a UD mill, sometimes listed as a cyclotech. We're going to grind that material, and we're going to power sieve that at a 1/4 millimeter size. And then we're going to do a second power sieve down to 0.18. And you may ask, why are you grinding it so hard? Well, the point is that the finer you grind it, the better homogeneity you can get. After we're done power sieving it the second time, it goes into this 10-liter cone blender here that you see at the left. Basically, we run that in 60-minute intervals for each one of the 4 materials. So you see this 5-step process, and we found over time that we have to do this to get the optimum homogeneity of our PT materials. Now, just to show you what we do, when we get done processing these, we run these out to an independent lab, and we ask them, we only pick 3 or 4 elements for analysis here, but we We run these through homogeneity testing. What we do is we pull out 3 replicates and we analyze each replicate in triplicate. So we have 9 values now that go into this database on the homogeneity. And you can see here from the last fall cycle, cycle 55, here are the 4 samples. Nitrogen ranged from 3 to 1% nitrogen air, but you'll notice on these standard deviations are just absolutely off the scale in terms of precision. The same for phosphorus and same for zinc. And it just shows you what the degree of processing that we put into our materials to make sure that they're highly homogeneous. Now, one of the things that we do is that our samples are packaged in 15-gram increments in a 2-ounce polystyrene jar, and we place these then inside a Ziploc bag. And this just to give you an example there at the right, you can see what an almond leaf sample looks like and what a bulk standard reference material that we offer. So just to make a point here is how much time do we push into the quality is. This is a comparison of what one of our competitors uses, a plastic baggie, a label on the outside. It really does not constitute a quality system. Now, of the materials that we've used since 2021, here is a list of 40 plant samples that we've used, and you can see it's very diverse in species. They go from potato leaves, almond leaves, spinach, canola, pistachio, banana leaves, spruce leaves, and in this last cycle in March, we had almond, buckwheat, and pumpkin and corn grain. The point behind the diversity in these species that we use is to get that analytical range. So when you look at these materials, you can get from low nitrogen to high nitrogen, low zinc to high zinc, and etc. Just to give you an example, we went through the database. We've run 192 proficiency materials since 2005. And these are the elements on the far left, the units, the number of results. This is the total number of analytical data that sits in the database across those 192 samples. And you can see we're in the tens of thousands of measurements here. But closely look at the min and max there. This is the lowest concentration of a particular plant sample versus the highest. So in nitrogen, from just over 0.1% to almost 7%. You look there at potassium from 0.16 to over almost 11%. And you go down to the page and you look at boron, 1.5 parts per million out to 236 parts per million. The point is that the samples we've ran through the ALP program over these last 20 years really represents a breadth of data set in terms of analytical concentrations, and i.e., therefore, you will have performance data, how you do through the analytical range. Now, our proficiency statistics is just a real brief slide talking about this, but we really look at that lab mean because each sample is analyzed in triplicate by a participating PT lab, and we calculate the grand median, and then we therefore can calculate the median average deviation. Okay, we use this because these data sets are not normally distributed. They do not follow that normal distribution, and because they have skewness to them, and they tend to be skewed to the right, to the high side, we find that the MAD calculations is far more robust. And then based on that MAD, we can calculate the 95% confidence limits of the median. And there you are, it's 2.9. Sorry that that symbol, the question mark, doesn't transfer sometimes from one computer system to another. But anyway, that's how we calculate those confidence limits. And then beyond that, because each laboratory measures their measurements in triplicate, we now have a measure of within laboratory precision based on a standard deviation. And we use a K statistic to flag labs whose repeatability, the in-house precision, exceeds a certain range. And this graph on the right here kind of gives you an idea symbolically about what that looks like, how we measure two things. We're measuring both the bias of your particular lab value from the consensus, and we also have a measure of your inter-lab precision. So we can tell you how well your precision is relative to your peer group. Now, this is phosphorus interlab data here. This is a phosphorus sample from cycle 55 last fall. It was a broccoli sample, whole plant. And you'll see there that in the center of that figure, you can see the blue line represents the median value, and the upper and control upper and lower confidence limits, which represents the boundaries around that. If you'll notice, we've ranked these from the lowest concentration to the highest concentration, just to kind of give you what that distribution looks like across there. You'll also notice the error bars on here. These error bars represents the standard deviation of each one of these labs measurements for phosphorus on that broccoli sample. And as you look across there, you see some very, very large error bars. Now, this sample ended up having a median concentration of phosphorus of about 0.42%, plus or minus 0.04 for the confidence limits. But you'll notice those labs with the white error bars. Because we've measured these in triplicate, we found that 5 labs had we had multiple labs with very large standard deviations. And in the end, there were 5 labs who had values that exceeded those confidence limits, and they would have been flagged for either low biased or high biased. If we look at that sample now relative to all the other samples that were ran in cycle 55, the other 4 plant species, you can see we had total phosphorus from just over 0.1% to well over 0.5 there. We've ranked these by that sample, the broccoli sample 2409, and you can see that all the labs, independent of where they are, if you rank them by that one sample, they all fall in nice trends across that graph. And that generally 39 of 43 labs provided phosphorus results within the 95% confidence limits. And lab 2409 showed higher interlab variability than the other samples listed in this graph. And labs 5, 31, and 42 overall across all 4 plant species had high interlab precision values. In other words, they exceeded the normal range by a K-factor analysis. If we take that data set, again for the 2409, and we just look at that standard deviations within a laboratory, okay, and we've sorted these, and you'll see this graph at the right, it really shows this distribution. And notice it's skewed to one side because, well, it ends at 0, right? Labs who get a very low, the 0 standard deviation is going to be at 0, so they extend to the right. And for this sample, you see that precision limit, in other words, lags failing for high or poor interlab precision, it ends there right around 0.03 concentration a standard deviation of 0.03. If you look at as a whole here, the average interlab standard deviation is 0.015, which is pretty remarkable considering that we had best decimal 42% phosphorus total concentration in here. So this is the importance of this, is that now we can provide you biased data against your peer group on any one of these analytical parameters for essential elements, but we also can tell you what your precision is. And I've got kind of a little more point on that later in my presentation. If we look at across the samples we've ran in the program for just last year, and we look at the median concentrations here for nitrogen and phosphorus, and then we have the within lab, intralab repeatability, that precision standard deviation, okay? You'll notice that as you go up in concentration, so too does the standard deviation increases Whiting wise. And this is really important to know because this is truly a function of quantitative analysis. That as you go up in concentration, your standard deviation starts to expand slightly. As you go down in concentration, it really takes off exponentially. And I'll talk a little bit more about that later. And at the far right column is reproducibility. And this is based on an ISO 57252 document. Basically, it can tell you how repeatability and reproducibility between repeatability within a lab and reproducibility amongst labs, how that changes as you go up in concentrations. And just to follow that up, it's the same type of table here we have for potassium and we have for boron. Again, as you go up in concentration, the repeatability within a lab increases, and so does the reproducibility. Now, one of the things I like to look at in these data sets is how does this work across a range of materials? How does these values change? And here I have listed a whole array of essential elements plus nitrate in the far left column. I have the interlab standard deviation for the 12 plant samples we ran last year in the ALP program for the 64 labs who provided us test data. And it's nice to look at these numbers, but really when we want to start talking about across plant materials, and we want to talk about just on a percentage basis, I've calculated the intra-lab RSD. This is the kind of the repeatability that we see as an average within laboratories across, again, 64 labs across 12 different plant materials. And you can see there nitrogen, phosphorus, 3-4%, 3 to 5%. That's pretty good. That's really outstanding. We get to potassium, and I have that highlighted in yellow. It doesn't play with the others. And partially this is because potassium on the ICP falls clear over at the far right of the spectrum at 766 nanometers, and it's just a little bit more noisy than what you have. Nitrate there you see listed at 35% RSD. Well, one of the reasons that is that of the samples we ran last year, the lowest nitrate sample was 20 parts per million, and the highest sample was 18,000 parts per million. And because that wide dynamic range, we get an inflation in that RSD. Zinc there at 8%, copper at 14%. And this was a bit of a surprise to me. Copper within a laboratory repeatability across these 12 samples was considerably more noisy than what the zinc or what we would consider adequate there at phosphorus and nitrogen. And obviously, when we get down here to molybdenum and nickel, 33 and 27, we're dealing with concentrations near instrument detection limits, and we have very few samples that have actual measurable quantities of those elements. So the interlab RSD grows exponentially. Now, when we take a look at lab performance, and I could show you graphs and all kinds of data on this, but I want to keep this very, very simple. So these are the 3 cycles from 2024 for the 12 plant samples we've ran through the system. And here's end combustion values for those 12 plant samples. And here are 4 labs. And I listed this here as delta nitrogen combustion. And what we've done, and we've taken each median value and we subtracted the lab value, whatever their grand mean was, from the grand median, okay? So 0 represents they got exactly the same number as the median, and then every deviations you can see there. And I only listed 4 labs because this gets kind of complicated to look at, but I think these 4 labs signify what's going on. So we see here we have labs with very consistent nitrogen analysis, i.e. the lab in green. Almost every value fell right along the median. We have labs with consistent high bias, both labs that are listed in red and black here. Again, they were very high biased. Actually, the lab color black there, it actually falls right down to the median value by the time we get to the last cycle. And then we have labs that are very inconsistent. And the lab listed in blue here, very inconsistent in getting values close to the median for samples 2401 through 2404. But boy, they sure cleaned up their act by the time they got to cycle 54 and 55. And it's really the inconsistencies that a PT program can help you find these things and identify them. Lab number 6 was inconsistent cycle 53, and then it improved. So that's what's going on here. You have these things that you pull back proficiency testing data, and you can actually show improvement in your operation. Now, I like to look at this repeatability thing because I think it's often missed in a laboratory. How well can you get the same number on the same sample that you're running on a regular basis in a laboratory? And here we have the same 3 cycles listed. We have nitrogen by combustion on the vertical, which is the interlab standard deviation. This is their 3 replicates they give us on each one of these 12 samples. And I've listed at the bottom here on the x-axis in gray bars what that average within standard deviation is for the 43 labs that participated. And again, I kept this to a handful of labs just because it gets to be a very complicated diagram. But results show that a majority of the labs have repeatability value, interlab standard deviations within the ALP database range. Lab number 18 there had multiple end precision issues, especially in cycle 54, noted by the red dots. Something must have happened in that particular laboratory in cycle 54. and their standard deviations just exploded. Uh, most point, all lab values are falling within the average, that window of average interlab standard deviations. And I'll go get a little more of that in a minute. If we look at a summary of performance for all 2024 plant samples we had last year here, you can see here nitrogen, there's a total of labs times samples times the number of replications we had here. You can see 476 total results. Number of lab results flagged for bias is 72. On a percentage basis, that's 15. Number of labs results flagged for poor precision is only 4%, 20 of that 476. If we look at the other analyses down the screen there, we see sulfur is kind of noisy. 18% of labs were flagged for biased. We look at potassium, also 4% were flagged for precision. If we look at the top three elements there, most of those values, 15% for nitrogen, 4% on within laboratory, those all fall within the ranges that we would see for all three elements. As you go down the page there, you'll notice like on number of lab results flagged for biased on molybdenum, it's 20% of the total database. Again, we're dealing with an analyte that's near the instrument detection limits of most ICP emission systems. And that corresponds into what we have happening with moly on the intralab. One surprise there, and I'm sorry, I'm going to have to move my toolbar here because it's in my way, is the copper. Again, I'm a little surprised. Copper is a very strong line in the ICP emission systems, and copper is also well within the detectable range in most samples that we're running here. To see this kind of noise in copper was a little bit surprising to me. Okay, and now it won't move. There we go. So one of the things I like to look in these data sets is how does these analyte concentrations, how does that impact the RSD within a laboratory, the RSD across laboratories? And here's a plot of nitrogen combustion concentration versus the interlab RSD across these 12 plant samples we ran in 2024. Now, all we did was take and convert the MAD, that measure of variance from the median there, and we converted that to a percentage basis for all 12 plant samples. And you can see this is a remarkably very tight correlation here because we ran samples from 0.1% nitrogen well out to 4% nitrogen. And this phenomena of the effect of concentration on the RSD is well known. It's noted as what we call the Horowitz trumpet. As you start to approach detection limit, the precision of the measurement literally starts to fall apart. And this is truly a classic diagram. And I make this point is it's remarkable to see such a strong relationship in PT data. Again, 12 very different plant materials ran through 43 labs. It's doing the nitrogen by combustion method. The interlab RSD follows a very similar type relationship and says that we have RSDs less than 3% when we have a nitrogen concentrations of 2 to 4% in a plant material. And it just shows you how good this particular method is across the 43 labs that do it. And it's interesting to note too, because they're running 3 different types of instrument manufacturers' combustion systems. Now, that's kind of a summary of what we've ran in the PT data. And I have a few comments here about improvements of analyses. One thing I think a lot of labs fail to do is to verify their detection limits and periodically re-verify those. And it's very, very critical on these low testing trace elements such as copper, molybdenum, and nickel. It's really important that you have that nailed down. It's not so important on phosphorus and nitrogen. For those labs who are running nitrogen combustions, I recommend calibrating with glycine P toluene sulfonate. I think it's a lot better standard to calibrate combustion instruments with. I've ran LECO 428s and 328s in the past. My problem with using EDTA is it's got a nitrogen concentration of 11.5%. That is so far out the range of what you run mostly for plant materials. Let's say you're trying to run a plant material that's 1.5% nitrogen and you're calibrating with something that's 10 times higher. This sulfonate's 5.66%. You can buy certified grade of this material from Sigma or any of the other suppliers. It really improves your thermal conductivity detector calibration. For ICP analysis, I'm sorry, I'm old school. I'm rigorous 5 standards minimum for running your calibration curves. And I think your low calibration standard is not 0. It's not the acid digest, but it's at 2 times your MDL concentration of whatever the analyte of interest is here. I also think it's important to include a low-end standard reference material with every analytical batch. You know, you've probably got a standard reference saw that you're using on your bench or something like that. I really prefer to have one in the lower range of your concentrations, because if it starts to move on the low range, it's probably going to move across the range as well. And then finally is develop a QC range chart daily, weekly to assess your interlab repeatability for all your plant samples. I'm not saying biased alone. I'm saying beyond biased, you're going to measure that interlab repeatability because it tells you what your precision is in your laboratory. Now, just a brief jaunt into a different area here. Corey asked me to kind of bring this because the tissue sampling season's coming on in the Midwest. And I just thought I'd throw this out for you. There's several publications out there for corn ear leaves. I've followed this kind of closely over the last 20 years. Purdue has one there listed. There at the left, at the right is the Reuter and Robinson's from their manual from 1997. Reuter Robertson, I like theirs a little better because it identifies deficient, marginal, sufficient. The Purdue gives you just a wide guideline. Now you can see for nitrogen there, they're fairly close. I mean, Purdue's 276 to 375 for nitrogen and corn ear leaf. I have a problem with Purdue's numbers for potassium. I think that 1.75 is well into the marginal range and that 2% is probably adequate. The Purdue data, I'll have to say this, part of that data set comes from the mid 1960s, and I think a lot has changed in corn production, and so therefore those numbers are a little bit skewed to the low end. And in terms of zinc down there, I have a real problem with Purdue. I do totally agree with Reuter and Robinson's 19 parts per million concentration on zinc is truly deficient. In fact, most of the guidelines now call 24 as the point where deficiency kicks in. I can tell you for a fact that I have data sets that show that until you get to 28, you're not in the optimum range for zinc. Just to show you how big deal deficiencies are in the Midwest here, this is a data set that I put together with 3 commercial labs from back in, I think at the period was 2014. I did this 2013 through 2015. And here's your deficiency thresholds based on, just pulling out numbers out of those values that came out of Purdue. And then I have Indiana, Wisconsin, and Minnesota. So there's 24,700 samples in this data set. And you can see here that in Indiana, 31% of the values fell below 2.9. And really across the Northern Corn Belt, those numbers pretty well held. It's about a third of the samples or a little more than a third of the samples are deficient in nitrogen. But move down to potassium. And if you throw a 1.9 as deficiency on there, a third of Indiana's over 3 years, over half of Wisconsin and Minnesota samples for ear leaves at R1 are deficient. It's a big deal out there. And if you look at zinc, you move across the Corn Belt from east to west, 50% of the samples are deficient in zinc based on a 20. And I can tell you, I think the 20 is far, far down in the low end. I think it should be a 24 to 28. My point here is that if you look at these 3-year averages, let's see that. There it goes. 3-year averages here. A third of the samples are deficient in nitrogen over this period, and almost half the samples are deficient in potassium. This is where plant analysis in the lab testing industry really can show benefit to growers about whether they had deficiencies or whether they addressed them or not. Kind of in summary here, plant analysis methods are based on quantitative analysis for these elements and chemical digestion for most of our metals and boron and molybdenum, with determination by ICP OES and by mass spec. Semi-quantitative determination of extractable ions is very important, maybe not so much in the Midwest, but when we move to the West Coast and we're talking crops like potatoes, we're talking vegetable crops, measuring nitrate, residual nitrate in tissues is a really big deal. In fact, most of the potato industry in the Pacific Northwest is all based around a nitrate analysis of potato petioles. Proficiency testing requires a diversity of species, a prepared sample, and homogenized, and an assessment of a lab performance. Proficiency results provide analytical performance across laboratories, both across laboratories and within laboratories. Now, just a couple high notes that I make note here from the ALP database. If you look at our 2024 proficiency samples, 85% of the nitrogen by combustion values were within the 95% confidence limits, an average of 6.5% of the median. Think about this. Of 43 labs doing the test, 85% of them had values within 6% of the median across the 12 plant samples we did. That is really saying two things. One, the instrumentation that we have for doing this test is pretty darn good, and that the labs who have those instruments know how to use them. If we look at sulfur and molybdenum, interlab results for 2024 had some of the highest number of lab failures, 18 and 26% respectively, and that they're generally, those failures all occur with high bias. In other words, they're all to the positive side of the distribution. We look at interlab RSD precisions for PK, calcium, magnesium. They average 4 to 5% across those 12 plant materials. I mean, it's absolutely amazing that the labs can do that method that well. And you have to also think about this. There's about 63, 64 labs that's doing these particular metals across the 12 plant samples. However, copper and molybdenum have the highest percentage of interlab standard deviations and therefore are flagged for precision. And then lastly, lab analysis, repeatability, and reproducibility improve with increasing analyte concentration. It follows our typical, what we expect, classical Horowitz trumpet. And it's pretty much true for most of the analytes that we talk about. Now, when you get flagged for biased or you get flagged for poor interlab precision in the ALP program, it really leads you to one point. You have to address your problem. And Alta has put together a presentation that we did back in August of 2023, and we call it Root Cause Analysis. It provides you the investigation framework for addressing lab proficiency failures. And that presentation, you can see, it's available at the Alta.ag. I'm sorry, I left the T out of Alta there, from the summer of 2023. And I think it provides you a general guideline about how to investigate bias failures and how to address precision failures. Now, I have to say this follows up to that intro slide I had. You cannot manage what you cannot measure. You cannot assess your measurement bias unless you know what your precision is. You know, I've always said to people, you do not know if you have bias if your RSD on your precision is 100%, because you have no idea where your forest or where your trees are at. So, with that, I'd like to make one last plug for the 18th International Symposium that's in 2 weeks in Durham. It's going to be a great symposium. Christian Hicks, Dustin Sawyer, Rob Mickelson, Luke Gataboni, and myself have put together a really great organization in terms of getting this thing off the ground. And considering we did not know that we were going to be putting this symposium on in March of 2024, it's outstanding how much has come together. So with that, I finished my presentation. Got time for questions, Corey?
Excellent, Bob. Thank you so much. That was a great presentation. When I reached out, so when our certification committee, asked for this presentation, I was afraid that we were throwing too much at you at once. And I think you took it all on. And now I'm a little worried that it was too much to consume all at once. But I think that was great. We do have a couple questions. I just want to lead off with and I'll say this, folks, if you have questions, let's put them in the chat and I'll make sure Bob gets to them. or you can raise your hand and Bob can answer them live. I certainly am not going to volunteer to answer any of these questions. But Bob, one, I will say this: I get this question as Alta president quite a bit, um, or at least occasionally, multiple times a year. You know, we soil test, but we don't plant tissue test. What are some first steps we can take if we want to start offering plant tissue testing? So I think a lot of labs realize that they have the primary equipment in the ICP, and so they're thinking I can do plant tissue testing, but I don't know how to even think about this yet. They think they have the staff, expertise to do it. They have most of the equipment to do it. So can you comment on that? What are, besides ICP, what are some key pieces of equipment, and like what should they be? How would you answer that question, Bob? I'll just leave it
Okay,
open.
the first premise is this. What is the objective of soil testing? Objective of soil testing, as I see it, is to say, okay, I have the nutrients in my soil. I have the right pH to produce a particular crop, right? So if I'm talking corn production in the Midwest, hey, I've addressed my acidity issues with lime. I've put in enough P and K starter into my system. I may throw in zinc and a 2x2 band, right? It's all looking forward down the road, right? Tissue analysis is a postmortem. A corn ear leaf at R1, you're never going to be, well, you'll have very little ability to manage that crop and make a change in yield by the time you get to that stage. Everything has happened, right? And so my point is about tissue analysis in corn and soybeans and wheat and these types of crops is it's a good assessment of how good your previous soil management was before, right? Now, the problem with tissue analysis is, one, it's very timely. You have to pull a sample at a particular growth stage. You have to get the right plant part sampled. So it takes a little more skill set or a different skill set than what it does for doing soils. And then it's a fast turnaround time. You people who are in the Midwest are probably not used to doing plant samples in 24 hours. But if you move to the California Pacific Northwest markets, tissue analysis is bigger than their soil testing business. It's probably 60% of the lab volume. And they're going to turn tissue samples around. They hit the lab at 4 o'clock, they go through the dryer, the grinder, and the results go out by noon the next day. Because in a lot of your vegetable crops and some of your tree crops, you can make a change in your nutrient planning or your nutrient management literally in hours. So in terms of instrumentation, I always look at it this way. If you have corn in the Midwest, you pull those ear leaves and you find out that you're well into the deficiency marginal range of nitrogen, you probably can kiss the farm goodbye, because you cannot really only change yield with nitrogen in corn by a little incremental amount, 30, 40 bushel the acre. And in terms of the rest of the elements, you can get an assessment of what you did was right or what you did was wrong. I always find that it's interesting that people soil test and then they wait till they get the grain tickets in from the elevator, about how well they did. And truly, plant analysis provides you a point to say, hey, I missed the mark. My yields are going to probably be down. I have a grower I actually do consulting for at Rising City, Nebraska. We go through his records every August, looking at his nutrient concentrations and figuring out, well, what's he going to tweak next year? What was the weather that affected this? So does that answer your questions, Corey?
No, I think that's great, and I think you kind of summed it up really nicely. It's complicated. And you have to think about what your intent is.
Yes.
I'm gonna go to this next question that was asked in the chat, and I love
You're breaking up, Corey.
this question because it gets to the core of a problem that run into. Question in the chat was, what are some good resources for crop nutrition deficiency charts? So you represent, or you shared Purdue, but what are some other?
Well, there's a plant analysis handbook, and I can't think, it's relatively recent. I think it came out in 2018. You'll have to text me or email me and ask me what it is. It's an okay book. If you want the classic Bible, as far as I'm concerned, it is Reuter and Robinson's book out of 1997. Gosh, it's dated, but it's a real catalog of every plant species that they've collected data on across the world. And it has like vegetables in it, corn, forages. It also tells you the conditions that the experiment was conducted to assess the deficiencies. But beyond that, it'll even tell you, okay, well, it was done in a greenhouse or it was done in real plots, and it'll even tell you where it was done at in the world. That book, it's truly an encyclopedia thickness. I mean, it's probably 700 or 800 pages. It is one of the best descriptions of how to sample plant tissues for analysis. In terms of the Midwest, and we talk about corn and soybeans, I got to tell you, there's no great place where everything has been put into one spot, talking about, and I'll use the word recent production. Sarah Six on their website under plant analysis has a relatively extensive section there about critical levels. I take a big sigh because most of the data is over 50 years old for your main crops. And we know so much has changed in that 50 years. Just a little analogy here for you for just a second. 1965, most phones were all dial, right? There was not the rotary phones. There was no push button phones, and forget cell phones altogether. And at that time frame, average corn populations across the country were 15,000 plants to the acre. And today we're planting 30,000, 36,000. So much has changed that I have real hesitancy about the interpretation of those critical levels. I'll leave it at that. I got too long-winded on this.
No, Bob, I love that response because I hear from agronomists all the time that they are kind of creating their own interpretations because they don't trust what the universities have out there. They just don't know where to go. And so, you got guys out there doing weekly plant tissue testing and coming up with their own curves and all sorts of things. And I love the innovation in this space, but also I have pause on how to advise people because it's hard to find solid data. So I
So,
love
so,
that. Go
so I,
ahead.
I was at the Commodity Classics. I interviewed two of these corn growers from the National Corn Growers Contest. And I asked them, I says, what do you use for your tissue guidelines for making sure you're in target for your, record corn yields? And all of them have built their own databases.
Yeah, that's what I hear from everybody. I have my own database that applies to me. Okay, so we have so first off, I'll highlight that there were a couple plant analysis handbook links shared in the chat. Also, next question was, how do you feel about and this is in quotes, new instrumentation coming into plant analysis, libs, XRF, NRI for nitrogen? Thoughts on new equipment, and then Bob, if you want to also add, I'll add onto that the SAP testing and your thoughts on SAP tissue testing.
Okay, so anytime we bring a new toy into the market, and I use toys, if you're a chemist, these are toys. Anytime you bring one of these to market, it has to go through that development phase. One is you got to get comfortable with. Two is you have to understand, is there any interferences I have to be addressed with? I think libs is pretty much primo choice here in terms of an instrumentation that could really work really well in plant analysis. Libs has two hangups, and I think that can easily be overcome. Hangup number one for libs is this. When you fire a laser beam at 10,000 C into a plant sample, you have to pre-package that sample. So you have to dry and grind just like we normally do. But then you have to compress it under high pressure, like thousands of pounds of PSI to form a pellet. And then they fire the laser into it. So there you got that extra step now in preparation. Number two is when you fire the laser beam into it, all that carbon volatilizes off as CO2, right? And so it creates a gas that basically perturbs the signal of the atoms that's coming back in that spectrum. And so it gets to be kind of complicated how you deal with the interferences that's created by that gas coming off. I think these are all easily overcome, but it takes technology a while to kind of cross that. Number two on the libs is that, you're never going to get nitrogen, right? It's basically an elemental scan here. Nitrogen, I think, can be done very, very well by NIR with a caveat. NIR models require rigorous model building and then they become very crop specific because of the reflectance that comes off when you you flash a light into the sample. So it takes very good calibration data. Hey, pick corn leaves, R1, you're good. Pick corn leaves at V5, going to get a different number. Pick corn leaves at later in the growth season, probably going to get a different number. And then you change crops and it changes again. So it requires a massive database. In terms of XRF, I think there's just as much possibility as Libs does. One problem with them both. You're never going to be able to measure boron with XRF because it's outside the spectral range, and you're going to have very difficult time to measure boron with a Lib system because it's such low detectable quantities. So all these new methods, they're not a panacea, but they do come they're going to have their place, I think. I will say this, I'm really interested about an instrument company coming to us that does Libs, NIR, and XRF simultaneously, because maybe that would rectify a lot of issues. I think the technology's there to do it. We have to find an instrument manufacturer that has enough private investment money to do it.
I was going to say that would be a very expensive instrument, Bob. But I appreciate those thoughts there.
Hey,
What
Corey,
about, yeah,
Corey, one caveat to that. Think about that. There are 2 Libs instruments operating on the surface of Mars on rovers right now. One's been there since 2011 and the other one's been there since 2019. If they can do that and they can build it the size of a shoebox, I don't think it's without the realm of the technology. It's the cost of development.
what about real quickly, Bob, your thoughts on sap tissue testing?
Okay, sap tissue. Okay, so in certain crops, this has already been developed, and we're talking garlic and onions, because if you measure the sap, which is a pretty fleshy tissue, you can measure nitrate, you can measure phosphorus, you can measure potassium. Now, when I was in California, a lot of this was done. It still is being done. It was never really sent off to the labs that much. It was done with cardiometers and other quick test things so that running a little tiny, like a size of a phone type thing, and you can measure. The next generation of sap testing has really come along in the last decade and a half. The problem goes back. I think we can do that. The question is 2 things. 1, what's the calibration database? And 2, how much is it going to cost? I think in specialty crops, vegetables, I think it's probably going to be a doable. If we get into corn and soybeans, I don't know. $10 beans, $4.50 corn, not so much. To me, a corn grower, if he really wants to focus on his mineral nutrition, and obviously he's got to have a soil test basis behind it, the next thing he does is he picks those good spots in his fields or history spots in his fields that have good, yield production, and tissue test those, and then tissue tests a couple of those places that he doesn't get very good corn yields. So
I love that strategy when it comes to sampling. I tell agronomists this all the time. Find good spots and bad spots in the same field and look at what the differences are. And that a lot of times can tell you how to improve those bad spots, how to bring them up. Because I always feel like that's where the profit is how do we get the bad spots up? So I think that's a good thought. So another question, have you done any analysis of results that distinguishes method of digestion, i.e. microwave versus block and tube or hot plate? And did you consider nitric perchloric, nitric peroxide, nitric hydrochloric? So, Bob, I know you have some thoughts on this kind of methodology. Do you want to comment on that?
yeah, I am no fan of perchloric. I did many perchloric digestions years and years ago. I do not like it. I can tell you that if you're running perchloric in your lab, you absolutely have to have a wash down hood system to remove the perchloric crystals out of that. When I was at Davis in another building on campus, they were dismantling the building, for demolition. And when they found out there was perchloric been used in one of the hoods there, they had to bring in a special team to disassemble the stack, the air handling stack that come off the lab benches there, because it was and just a sidebar, guys, this is nothing to laugh at, because back in the late 50s in El Paso, Texas, the chemistry department those perchloric crystals detonated in the stack and blew out half the side of the building. So this is nothing to laugh at. I'm no fan of perchloric. I think for plant digestions, nitric and peroxide, nitric and hydrochloric are fine. You asked me if I compared results. I can tell you this: wet open digestion, wet microwave digestion. For most of these elements, there's no differences within the biased, or there's no differences within the interlab. Having said that, when you get into the micronutrients, boron, molybdenum, nickel, these types of things, the microwave numbers stand themselves apart because it's closed vessel and you have minimal contamination. And I generally say this: labs who employ microwave have a little higher standard on their ICP analysis. They're really paying a lot more closer attention. Dry ashing, I can tell you this: when I took over the lab in Davis, God, 30 plus years ago, we had dry ashing. That's how we prepared all our samples. The problem with dry ashing, it's a much lengthier digestion. You're talking about hours in a muffle furnace. Number two, muffle furnaces have memory problems. In other words, as stuff burns off, the carbon burns off, some of those elements go into the brick and the fire brick, and then when you run a low sample afterwards, you get the stuff coming back out of the fire brick. The whole reason I went to microwave back in the 90s is that we convinced our power requirements for our campus electrical system people that we could cut our electrical consumption by about a third by getting rid of muffle furnaces. So
I appreciate that response, Bob. I think it's a complicated topic, and I love your highlight there of safety, because I think sometimes as a lab organization we don't always think about the safety issue, but there is safety issues with what we do. So that's a good thing to be aware of. So with that, I don't see any other questions. I want to thank Bob today for today's presentation, and thank you all for being able to join us. I will highlight that the Alta Summer meeting will be in August, and this group, everyone that's on today, will get a link. We'll share how to register and learn more about that event. But that said, thank you all for joining, and have a great day.
take care, everybody. Bye.